Welcome to part 2 of lecture 16. So we're going to start by recapping the multiplicative weights guarantee and reformulating it a little bit. So last time we thought of, when we talked about the online learning model, we thought about the algorithms for that model and multiplicative weights in particular as producing, as taking like some action at each time step, which was selected according to a probability distribution. And we thought about how to bound the expected regret of the algorithm over the course of its execution. Today, we're going to take a slightly different perspective, which is really equivalent, but is going to be sort of more useful for us, which is we're going to think of this, the online algorithm decision maker as simply taking, producing a single, a vector of a distribution over decisions. And like its action will be that distribution rather than a single action chosen from that distribution. Okay, so the picture you should have in mind is that, here's the learner, let's say the multiplicative weights algorithm. At each step, it produces a distribution. So this is in a distribution over the M possible underlying base actions. And there's a little bit of a notation switch, sorry here. Last time we used K, this time today, for reasons that will be clear, we're going to use M as the number of actions. Okay, and now then the adversary, so out here is the adversary, produces a cost vector, which is a vector of length M with numbers between 0 and 1. And then the algorithm produces another probability distribution, gets another cost vector back, and so on and so forth. T, and gets back cost vector T. Okay. All right. And so this model makes sense when the thing you're thinking, the thing you're using to produce the algorithm is actually a vector. And actually, in a lot of the applications of online learning, that's really the right model to have in mind. So for example, in various optimization problems where you're doing some online to batch conversion, the way that you're using the online learner is to produce a vector, parameter vector for some optimization problem you're trying to solve. And today we're going to see an example of that. But like maybe going back to the motivating examples we had for multiplicative weights last lecture, if you think of like the stock investment setting, you can think of the action I take at on each day is I invest in a portfolio of stocks. So I take my $1 that I wanted to invest, and I distribute it among a bunch of different stocks, right? I might, presumably, usually investing more. So like my $1 billion that I want to invest if I'm running a hedge fund, and I'll spread it among a bunch of different stocks. And so really what I'm playing is not a random stock chosen from that distribution, but like that portfolio of stocks. Okay, and the theorem we get for this view of things is actually quite nice, and it avoids probability entirely. So, so the theorem is that for all strategies that the adversary chooses, and now we're going to measure regret with respect to the best probability distribution in hindsight over actions we could have chosen in hindsight. So for all probability distributions over the M base actions, we get that the sum over the average over all time steps of the cost we pay, which is now the inner product of the cost vector and the probability vector. So this thing is the same as the expectation over an action chosen according to P of the cost of that action, but we're going to just think of it as sort of more abstractly as this inner product. And we're going to compare to the best distribution we could have used in hindsight. Had we known all the cost vectors ahead of time, what single distribution over actions would we have chosen? Okay. And what the theorem is that this has the same regret bound as what we had before. So now log of what is now m over t. Okay, and there's no probability in this statement at all. This is with this holds with probability 1, which is like pretty cool. Like it always holds. It's not really a probabilistic statement at all. Okay, so I'm not going to really go through the proof of that. It's basically the same proof we did last time. So the proof just sort of uses this, is basically encoded in the proof of the main theorem from last time. So you just look at equation 10 in the notes, and it basically shows exactly this. The only hitch here is that now we're measuring our performance relative to this base action, relative to a distribution of actions in hindsight. But it turns out that's really just like a notational thing. It doesn't really change the meaning of what it means to look back in hindsight. And that's because the best distribution in hindsight is in fact a base act, like puts all of its mass on like the best action. Okay, so actually, sorry, I realized I've got like a little bit of a mistake here in my notation. So here, what I wrote was like true, but this is the form I want to use. It looks more like this. Okay, so for any p star we could choose ahead of time, for any p star we might have chosen in hindsight, the regret with respect to p star is bounded by log of m, square root of log m over t. And the reason that like the p star doesn't really change anything is that if we look at, this quantity, so this t equals 1 to t of ct p star, the cost of p star, that cost is actually just the expectation over an action chosen according to p star of the cost in hindsight of the action A. Okay, so that's just by linearity of expectation. Sorry. And so this is always going to be like no better than the minimum, the cost of the best action in hindsight. Okay, so we've so QED. So we're measuring regret with respect to p star, but p star is really no better than the best single action in hindsight. And so the same theorem, same proof we had before will work here directly. But this vector perspective is going to be useful to us. Okay, so that's all we need to remember about the multiplicative weights algorithm. We don't really need to remember how it works, just that it has this very powerful guarantee, and that's what we're going to use. And so after the break, we'll come back to differential privacy and start looking at the query release problem.